Hello students, welcome to grade 12 chemistry revision lesson on entropy and the second law of thermodynamics. In our today's lesson, we will learn about entropy and entropy change, the second law of thermodynamics, free energy and free energy changes. At the end of this topic, you will be able to define entropy and entropy change, calculates entropy change, states the second law of thermodynamics, define free energy and free energy change, calculates the standard free energy change, describe the relationship between standard Gibbs free energy change, standard enthalpy change and standard entropy change of a reaction. Students, if you are ready, then we will get started. Entropy and entropy change. Entropy is denoted by capital S and entropy change denoted by the symbol delta S, entropy change. Entropy is defined as it is a measure of the degree of randomness or disorder of a system. Entropy is a measure of the degree of randomness or disorder of a system. The greater the randomness or disorder in a system, the highest it is entropy. The entropy change, delta S, is the measure of the increase if delta S is greater than 0, or decrease if delta S is less than 0 in disorder of a system that undergoes a change. The change can be physical change or chemical change. That means chemical reaction. Examples. Decide whether the following becomes ordered or disordered. A. Solids melt to liquid. This process is disordered. Therefore, change in entropy, disordered. Change in entropy delta S is greater than 0. The sign of delta S is positive. B. Spreading of perfume in a room. Now this process is disordered. Delta S for this process is greater than 0. The sign of delta S is positive. Repairing a broken radio. Now this is ordered. Change in entropy, delta S is less than 0. The sign of delta S is negative. Solids or liquids dissolve in a solvent to form solution. Again, this process is disordered. The change in entropy, delta S is greater than 0. Sublimation of naphthalene, disordered. Delta S is greater than 0. Explosion of nitroglycerin, disordered. Change in entropy, delta S is greater than 0, and the sign of delta S is positive. Therefore, entropy is the measure of degree of randomness or disorder of a system that undergoes a change. The entropy change, delta S, for a chemical change is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. For reactions of the type AA plus BB to form C plus D, the change in entropy, standard entropy change, delta S naught of this reaction equal C times molar entropy of C plus D times molar entropy of D minus A times molar entropy of M minus B times molar entropy of B. If delta S for this reaction is greater than 0, now there is an increase in disorder of the process. Delta S greater than 0 indicates an increase in randomness or disorder during the change. Delta S less than 0 indicates a decrease in randomness or an increase in order. For example, hydrogen gas reacts with oxygen gas to form water. Molar entropy of hydrogen is 135.57 joule per Kelvin. Note that the SI unit of entropy is joule per Kelvin. Molar entropy of oxygen is 205. Molar entropy of water is 69.91 joule per Kelvin mole. And temperature is 298 Kelvin. What is S? The change in entropy, delta S, for this reaction, for the given reaction, equal 2 times molar entropy of water, 2 times molar entropy of water, minus 2 times molar entropy of hydrogen, minus 1 times molar entropy of oxygen, equal 2 times molar entropy of water is 69.91, 69.91 joule per Kelvin, joule per Kelvin. Mole will be cancelled by mole. Minus 2 times molar entropy of hydrogen is 135.57 joule per Kelvin. Minus molar entropy of oxygen is 205 joule per Kelvin. Now this gives minus 36.35 joule per Kelvin. You see, it's negative. Entropy change delta S is less than 0. You see the change from gas to liquid. The second law of thermodynamics, the connection between entropy and the spontaneity of a reaction is expressed by the second law of thermodynamics, which states the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. The second law of thermodynamics states any spontaneous change that occurs in the universe must be accompanied by an increase in the entropy of the universe. That means change in entropy of the universe, delta S of the universe equal change in total entropy, total equal change in entropy of the system plus change in entropy of the surrounding, greater than 0. According to the second law of thermodynamics, if total entropy change is greater than 0, then the process is spontaneous process. Note that there is no cut criteria for the sign of entropy of the system and entropy of the surrounding, as long as total entropy change is greater than 0. Therefore, if total entropy change is greater than 0, then the process is spontaneous process. If total entropy change is less than 0, the process is non-spontaneous. If total entropy change equals 0, then the process is equilibrium. We can write this as entropy total, delta S, total entropy change equal change in entropy of the system, delta S of the system, minus change in entropy of the surrounding is directly proportional to enthalpy of the system, delta H, but inversely proportional to Kelvin temperature T, greater than 0. This is the second law of thermodynamics. Free energy and free energy changes. Free energy denoted by the symbol G, capital G, and free energy change denoted by delta G. A new quantity that tells us whether a reaction will be spontaneous was first developed by the American mathematician J. Willard Gibbs. He proposed a new state function now called the Gibbs free energy change, or just free energy, designed by G. The Gibbs free energy change enables us to know whether a given reaction is spontaneous or non-spontaneous. The Gibbs free energy change relates enthalpy change and entropy change through this equation. Delta G equal delta H minus T times delta S. Note that from the second law of thermodynamics, we have this total entropy change, delta S total equal change in entropy of the system plus change in entropy of the surrounding equal change in entropy of the system minus change in entropy of the surrounding is delta H divided by temperature equal total entropy change total. If you multiply both sides by temperature, now T times delta S total equal delta S of the system minus delta H. This will be cancelled by this. This become temperature. Therefore, this is the same as T times delta S of total equal temperature T times delta S of the system minus delta H. Now multiply both sides by -1. Now this become minus. This become minus T times delta S plus delta H. Minus T times change in total entropy change is the Gibbs free energy change denoted by the symbol delta G. Delta G equal delta H minus T times delta S of the system, which enables us to know whether the given reaction is spontaneous or non-spontaneous. If the Gibbs free energy change delta G is less than 0, then the reaction is spontaneous reaction. If delta G is greater than 0, the given reaction is non-spontaneous. If delta G equal 0, the reaction is equilibrium reaction. The following can be summarized for delta G equal delta H minus T times delta S. 1. For a change in which delta H less than 0 and delta S greater than 0, the change in Gibbs free energy change becomes less than 0. Delta G is less than 0 and the process is spontaneous. We said the Gibbs free energy change delta G relates delta H with entropy through this equation, T times delta S. Here it says delta H less than 0 is negative, delta H negative, minus delta H. Delta S greater than 0 is positive, positive times negative is negative, minus T times delta S. Negative plus negative is always negative. Therefore, the Gibbs free energy change delta G is less than 0 for all temperature. 2. If delta H is greater than 0, delta G equal delta H minus T times delta S. If delta H is greater than 0, it's positive, delta H, and delta S is less than 0, negative, change in entropy, negative times negative is positive, plus T times delta S. Now this is always positive for all temperature. Therefore, the Gibbs free energy change delta G is greater than 0 and the process is non-spontaneous. 3. If delta H is greater than 0, delta H greater than 0 and delta S greater than 0, delta G may or may not be negative, but only if delta H is less than T times delta S, delta G less than 0. 4. If delta H is less than 0, negative, and delta S less than 0, negative, positive. Delta G is less than 0 if T times delta S is small. This occurs at small values of temperature. For the reaction AA plus BB to form CC plus DD, the standard Gibbs free energy change for this reaction, delta G naught of the reaction equal C times delta G naught formation of C plus D times delta G naught formation of D minus A times delta G naught formation of N minus B times delta G naught formation of B. Note that the standard Gibbs free energy change for an element is 0. For example, calculate the standard free energy change for the reaction silver sulfide plus water gives silver plus hydrogen sulfide plus oxygen. Standard molar free energies of formation of silver sulfide is 40.7 kilojoule. For water, minus 237.2, and for hydrogen sulfide, minus 33.6 kilojoule per mole. You are asked to calculate the standard Gibbs free energy change for this reaction. Now, delta G naught of the reaction equal 4 times delta G naught formation of silver is 0, because the standard Gibbs free energy change of an element is 0, plus 2 times delta G naught formation of hydrogen sulfide is minus 33, minus 33.6 kilojoule, plus 1 times delta G naught formation of oxygen is 0, minus 2 times delta G naught formation of silver sulfide is minus 40.7 kilojoule, minus 2 times delta G naught formation of water is minus 237.2, minus 237.2 kilojoule. Now this is delta G naught of the reaction. The standard Gibbs free energy change for this reaction is plus 488.6 kilojoule. You see? Delta G naught is greater than 0. Show that this reaction is non-spontaneous. The reverse process is spontaneous. Students, let us practice this exercise. You have 3 minutes. Good. Let us do together. Given the following delta H and delta S values, determine the temperature at which these reactions would be spontaneous. M, delta H equal 10.5 kilojoule, delta S equal 13 joule per Kelvin. For what temperature this reaction would be spontaneous? We said the Gibbs free energy change, delta G, relates enthalpy change and entropy change through this equation, delta H minus T times delta S. Now delta H is positive, delta S is positive. If the reaction is spontaneous reaction, delta G must be less than 0, less than 0. This is the same as delta H is less than T times delta S. T times delta S is greater than delta H. For T greater than delta H over delta S, this reaction would be spontaneous. For T greater than, for temperature greater than, delta H is 10.5 kilojoule. 10.5 kilo is 10 to the power of 3, 10 raised to 3 joule divided by change in entropy. Delta S is 13 joule per Kelvin. 13 joule per Kelvin. Joule will be cancelled by joule. We are left with Kelvin, which is the units of temperature. Therefore, for T greater than 10.5 times 10 raised to 3 divided by 13 Kelvin, this reaction would be spontaneous. B, delta H 1.8 kilojoule, delta S 113 joule per Kelvin. For what temperature this reaction would be spontaneous? Again, delta G equal delta H minus T times delta S. Delta H is positive, delta S is also positive. For this reaction to be spontaneous, the Gibbs free energy change, delta G must be less than 0, less than 0. We can write this as delta H is less than T times delta S. Or T times delta S is greater than delta H. For T greater than delta H divided by delta S, this reaction would be spontaneous. For T greater than delta H is 1.8 kilojoule. 1.8 kilo is 10 raised to 3 joule divided by delta S is 113 joule per Kelvin. Joule will be cancelled by joule. For T greater than this reaction would be spontaneous. C, delta H minus 11.7 kilojoule. Delta S is minus 105 joule per Kelvin. For what temperature this reaction would be spontaneous? Again, the Gibbs free energy change, delta G equal delta H minus T times delta S. Now the sign of delta H is negative. This is negative, minus delta H, minus delta H. Delta S is also negative. Negative times negative is positive, plus T times delta S, T times delta S. For this reaction to be spontaneous, the Gibbs free energy change, delta G must be less than 0, less than 0. Multiply both sides by negative 1. We can write this as delta H minus T times delta S is greater than 0. For delta H greater than T times delta S, delta H is greater than T times delta S, or T times delta S is less than delta H. Therefore, for temperature, for T less than delta H divided by delta S, this reaction would be spontaneous. Delta H for temperature less than delta H is minus 11.7, minus 11.7 kilojoule, 10 to the power of 3 joule divided by delta S is minus 105, minus 105 joule per Kelvin. This reaction would be spontaneous. Good. Students, in our today's lesson, we discussed entropy. Entropy is the measure of the degree of randomness or disorder of a system. The second law of thermodynamics states the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. If total entropy change is greater than 0, then the process is spontaneous process. We learned free energy and free energy change. The Gibbs free energy change enables us to know whether the given reaction is spontaneous or non-spontaneous. If the Gibbs free energy change is less than 0, then the reaction is spontaneous reaction. If it is greater than 0, the reaction is non-spontaneous reaction. If delta G equals 0, the reaction is equilibrium reaction. This brings us to the end of our today's lesson. Until next time, goodbye.